can start with the medical imaging. So hello, I'm Michael Chich from the Medical Informatics. And today we talk about a little bit two imaging modalities. One is ultrasound, the other is MRI. I skipped the ionizing things like X-ray, CT, PET, SPECT due to a matter of time because we have only 45 minutes to go briefly in these techniques. So the idea is really more from atom to the image, less medical interpretation, more the physical technical background. Yeah, thing is ultrasound, and just have a smooth introduction. So just for definition, ultrasound is everything above 20 kilohertz. This is our range of hearing that we can't really go with our ears beyond this 20 kilohertz. And in the general context for this lecture, different terms, sound waves, compression wave, longitudinal waves, they all mean the same. They just come from different directions. So basically, ultrasound is well known from the bats that send some ultrasound waves and travels through the cave or anything else. You have some reflections and receive the echo to get some three-dimensional for the bats feeling for the environment. And more or less the same as with ultrasound. We have ultrasound transducer replacing the bat, sending some ultrasound waves, will receive some echoes and can generate our image. So sonography, the medical application of ultrasound, starts at a higher frequency, so roughly from 1 kilohertz up to 40 kilohertz, depending on the application. And the same principle is exactly the same. So most important is the physics behind this, how this sound waves interact with the tissue, what is the reflection, what is scattering, what is the attenuation, and so on. And ultrasound developed since the start, roughly 1950, a lot. So you see the comparison of this baby, the image quality from the image where we're in the beginning to what we see now, where we have really detailed and sharp resolution. So next subchapter is physics behind this. Most important, okay, what is a longitudinal wave? So this is a nice example. We have a wave traveling from left to right. We have a particle movement, which goes also in the right direction. However, the net movement of the particle is zero, so it stays over time in average at the same place. The most important equation for ultrasound, I think this is the only equation you really have to remember for ultrasound, is that the ultrasound speed of sound is the wavelength number times the frequency. Means if the frequency increases, assuming constant speed of sound, the wavelength is decreasing and vice versa. For rough orientation, we have different sound speeds and different kinds of tissue. We have the air, roughly 330 meters per second. We have soft tissue with about 1,500 meters per second, bone with higher speed of sound. And as I mentioned, the ultrasound frequency is in range of megahertz. Therefore, our wavelengths, which is important for image resolution, is in range of hertz. So then we can send our ultrasound wave, and we have several interactions within the tissue. The most important one is reflection. We have also scattering, attenuation, and there are minor other ones that are not so important. Yeah, first thing is reflection. Reflection appears on a tissue boundary where transmission from one tissue to another. And this means we have partially reflection, we have partially transmission, and we assume that the entire energy is preserved, so we don't have any loss. So what's not reflected will be transmitted. And again, we have the three kinds of tissue. We have the soft tissue, fat, water, brain, muscle, and a lot of other things, with more or less a similar speed of sound C, more or less a similar density. And we have this other air and bone, which has different behaviors, properties. And then we can calculate our reflection coefficient, which is based on the speed of sound and the density, to detect, okay, how many density energy will be reflected. And this is within soft tissue only 0.5%, which means nearly everything will be transmitted. Once we have the ability to build in the tissue, we don't reflect everything and don't transmit anything. This is a little bit different for soft tissue and bone interfaces. Here, the amount of energy reflected, and for air, which is about any mean for ultrasound, we have probably 100% reflection. Therefore, ultrasound in lung, ultrasound in colon is really challenging. The next interaction will be scattering. Here we have small structures in the body, could be a vessel, could be a liver lobe, could be kind of inhomogeneity, and then we have scattering, like we know from scattering in waterways, in water. And you see we have also a wavelength in the range of the scatter distance, scatter diameter, and create some interference pattern. And this interference pattern is this what the ultrasound makes it typical for a visual appearance. So if the wavelength matches roughly the structures, then we see a specific pattern. On the left side, the ultrasound image. On the right side, you see a sketch where the liver, where's the kidney, the holes are vessels. And at the end, we zoom in a little bit. You see this pattern, this speckle pattern, which is the interference pattern. This is characteristic for specific types of tissue. So if you get used to it, then we see really, okay, this pattern is more liver-like, this pattern is more muscle-like, and it's stable. Even stochastically, it's stable. So if the tissue is moving, we see a constant moving of this pattern, so we can track them for tissue tracking. The last one of the interaction is absorption. That's a quite common absorption. We have friction, we have transferring the mechanical wave energy, thermal energy, and the intensity is ultrasound. Staying through pathways with time of light. Here are also some values. So you see for lower frequencies, because its attenuation is frequency dependent, we have higher penetration. And if you go with a frequency up to about 40 megahertz, we see that we can only penetrate about 6 millimeters in lesion. This determines our application. So we can't go with 40 megahertz in liver imaging, because liver we need 10, 15 centimeters, and this is visible with this technique, so this is frequency range. So this is important. So, okay, we have to choose a wide frequency, depending on the organ we want to investigate. So only based on this table, we say, okay, we can always use the lowest frequency as possible, because we need high penetration, but later we come to the resolution part, and therefore we observe the opposite, that higher frequencies have a lot of advantage. Yeah, if you have the absorption, our ultrasound image will look like this. So we have high intensity in the near field, so the transducer is placed here on the top, and the wave is propagating in an axial direction, so in left. And we don't see anything, and therefore they introduce the time gain compensation. That's just an amplification, which is depth dependence to make the image less homogeneous in terms of intensity. So this was the first part about the physics behind this, and maybe we spend 30 minutes for digest this a little bit. If you have some questions, it's a good time to start this.
Does it depend on anything else? Just frequency, wavelengths?
Again, what is
Maybe does the phase matter?
the phase of the wave?
Yeah.
No, it's not. The most important thing is frequency. Yeah, or the pressure, the intensity, of course, but then you're limited in safety reasons.
If I scream really loud at a stomach, can I gain some information?
If you scream,
and someone records me, like the whatever comes back.
first of all, you will see a lot of movement, which disturbs your image.
I mean, the person might run up. I scream at their stuff.
You scream what?
If I scream at someone, they might move. Right, that's irrelevant.
Yeah, I don't really get the idea. So you scream,
I mean, no, I was just saying, like, is screaming in the range of like something that works?
No. Screaming is in the audible range, which is up to 20 kilohertz.
Right.
And this one is 1 megahertz. So there's no interaction between both. Right. You will, only see interference if you have something in the same frequency range, vibration, which is, not happen in the normal way. Yeah. Only if you have two ultrasound devices at the same place. Okay. Second part. Now we switch a little bit from the basic physics to the ultrasound transducers. So this is a typical ultrasound transducer. And there are a lot of different types. Different types. We have linear array, convex array, this is by the way the convex array, we have space array, and so on. We have also applications for internal, the endovaginal, transesophageal transducers, and they have, of course, different applications, different properties. However, the basic concept is always the same. So this is how it looks in a really, really simplified way. We have the most important one is the piezoelectric layer. This is used to convert the mechanical energy to electrical signals and vice versa. And transmission layer to transmit the waves directly to the body. We have some buffer to avoid unwanted vibrations and noise. And since we have the piezoelectric layer was used for transferring energy from mechanical to electric and vice versa, they can only send or receive signals. But they can do both. However, then we have interference and don't see anything. It's the same thing as two people talk to each other at the same time. It's really hard to understand anything. So we can, in practice, we should avoid to do both at the same time. We can send, we can receive one after each other. And the field of the ultrasound, this is the intensity or pressure field from an ultrasound wave. From its transducer is shown here, high intensity. Red is high ultrasound pressure, and you see three different areas. In the near field, closer to the transducer on the left side, you see high intensity but high heterogeneity in the field. On the opposite side, on the right side, you see a smooth field, homogeneous but low intensity, and in the middle we have the focus spot. This is where we want to measure. We have really small, intense area in the lateral from the point of ultrasound, but it remains up, down, and a good distribution in the axial direction, which is here left, right, always from the point of view from the ultrasound transducer. So the focus is the place where we want to measure, where we receive the best signal, and the focus distance from the transducer is depending on the shape, this is heat, it's from the ultrasound frequency dependent, it's from the ultrasound speed dependent, however, it's more or less constant. If you use this setup, you have one fixed focus, depending on the transducer geometry, and we have to stay with this forever. But if you want to go with deeper tissue, with tissue more superficial, then you can use a phase area principle, where we have different ultrasound rings or different elements which are used with a small delay. So the outer parts are activated early, the inner parts activate a little bit later, so we have beam steering of this ultrasound wave, that we can use our focus at the point we want. So it's a dynamic focus in sending. Used to get a sharper, higher quality image. At the same time, we have the dynamic focus in receiving. So we have here different ultrasound elements, and you see a reflection from a small scatterer arrives at different time points due to different time of flight. So the time of flight here from the scatterer to the middle element is shorter compared to the outer element. You see the signal has different arrival time, and therefore we use a delay, which brings all in line, and then we sum up the signal from all elements to create the most sharpest. This delay is not only dependent on the piezo element, it's also depending on the depth of the signal or the time of flight, so it should be changed a little bit depending where we are. Both together brings us image quality. There are techniques which use only one to have, for example, a higher frame rate or whatever, but this is a common principle. So I still introduce a little bit this resolution thing, which is in relation to the wavelengths. It's more in the actual direction. It's also in the relation, or depending on how good we can focus our ultrasound beam, geometrical thing. As you see here on the right side, the corresponding resolution. It's roughly in the range of millimeter, and it is highly frequency dependent. This is the opposite side. The penetration depth from ultrasound decreases with increasing frequency. The resolution to the opposite. So you have always to choose a good frequency for the application we want. If we want to go deep in the tissue, we lose resolution because we need higher frequencies. If we want to measure only the skin, we can use higher frequencies. Don't need high penetration. Then create a better image in terms of resolution. So this was the second part. And before we start with the next part, we can have time for one or two questions. Yes?
I was wondering the different shaped, I can't remember what they're called, but
Or the ultrasound transducer shapes.
yeah, exactly. What would be the different uses of them?
So come to this in the next slides. We have here a transducer which is curved. It has the ability to create an image like this. So it's an image with a wide lateral view. You get a good overview. There exist other transducers with a flat surface. You only have an image like this. So you lose a lot of space in white light, but you create a better resolution. So this is application for abdominal organs where you need this overview part, and the other one more for the visual organs like the thyroid, the skin, and face area. This was one of the. This one has a very small footprint. This is a footprint, the gray area, and this is used to go for cardiac application. Because if you have the ribs here, you can place the transducer along the ribs, but then you're unable to rotate this. And with the face area, you have a small footprint, you're free to move everything. So 3D ultrasound is used, as the name suggests, create a 3D image, mostly for digital images. And the other neurovaginal transducer focal is also a small piezo in the beginning to come. You don't use a lot of space. Yes?
Does it spread the image?
Yes.
Using does the image spread? Like when you're looking back, would it spread parts of the image along the axis if it's taken by a
Yes, so it's spread. So the lines of image are not in a linear transducer, lines are parallel to each other. In this convex transducer, you have spread lines, so the distance between the lines increases with more the opposite with steps.
Right.
So the image quality is decreasing, but you have this overview.
The spatial resolution also depends on the density of the upright of the receivers.
No. You have two kinds of spatial resolution. You have the nominal resolution, just to pixel spacing. This is highly dependent on the line density. But you have the effective resolution where you can distinguish two objects from each other. And this is more
Frequency.
Frequency, yes, and the ability to focus this. How many? So there is not only a single piezo element. Here are about 120, 200 elements included, and you don't use all this all together. You use only the power.
So in the slide, you mentioned that the sonography functions from 1 megahertz to 40 megahertz.
Yes.
But then your table starts from 3.5 megahertz. So what can we see with a 1 megahertz sonography?
Can also go with abdominal images. So it's not that you exactly have to use this frequency. So it's more an overview for a comparison which values correspond to which for the absolute values. For the application, if you go to liver and so on, you sometimes want to have a small person, people who we don't need 15 centimeters penetration depth and can adjust it a little bit. In the latest ultrasound devices, you can't use the frequency directly. You just say, okay, this is my highest penetration depth, and then the program automatically adjusts the most proper.
Usually, you need like an oil over the skin to
You need
increase
ultrasound gel, yes.
Okay, this is in order to increase the
It's
contact.
yes, the contact is the thing. So as I said, air is the most problematic thing. You have full reflection. If you have between the transducer and your body a little bit air, even if it's only small bubbles, you lose a lot of signal. You could use water. This was in the very beginning of ultrasound. You sit in a bed of water, but it's not convenient. And therefore, yes, a small gel, which is just for coupling the ultrasound and to know you if it's good.
Yeah.
Okay, so we can go further. So now we go really to the image things. We start with the anatomical image. This is the most common thing, just to see spatial arrangement of organs, for example. And here we start with a very, very simple mode. This is called A mode. It's not used anymore, only for ear measurement. But yeah, it's a nice thing to start with this. So we have the transducer, we have the pathway along the axial direction of the ultrasound waves. This is the dashed line. The ultrasound passes the right ventricle, left ventricle goes to the left atrium. And then we have always at the tissue boundary, with all the small black lines, some reflection. And within a more or less homogeneous tissue where we have a lot of scatterers, this is the gray, but we have the scatterers. And we receive a lot of echoes. We have always a pathway, we have go here, have reflection, and we also go here, have a reflection, come back. So the time of flight is what we basically, in the first order, receive as corresponding and the corresponding signal intensity. Then we can just assume a constant speed of sound, C. The typical value is 1540. And then we can calculate the corresponding depth by assuming this constant speed of sound. Then we see here the A mode. The signal signs this will be refreshed in real time and get some first impression. Okay, where is the structure? Where is no structure? Here we have the problem here when we can send the next pulse, because we can't use those sending and receiving at the same time. And for example, if you have two tissue boundaries, so the right doesn't correspond to the left image, it's treated separately, we see that the first echo is quite high. The second echo from the second tissue interface is reduced due to the absorption. Now, if you start second pulse in sending, we receive obviously the same echo, that's the same time of flight. And surprisingly, the first echo from the second push pulse matches with the second echo from the first push pulse. However, the amplitudes are quite different since we have this absorption in the amplitude. So we only see what we send it at the second time. There's no main interference between those. And this determines how deep we want to, or how deep we want to look, determines how fast we can refresh our signal. So this is called the pulse repetition frequency, and it's typically in the range of several kilohertz. So to extend this a little bit, we can create an image instead of a signal. So we just report the intensity of the signal and draw it over the time and see a picture where everything is moving over time. Quite easy, nothing special, and it's used mostly in the cardiac application where we have some movement. Here we see over the cardiac cycles, that's the left ventricle, this part here, or corresponding to this part here. So the dashed white line is exactly the image that is changing in volume, and then we can derive some quantitative values, maximum diameter, minimum diameter, and so on. Here, the high refresh rate of several kilohertz is quite useful because the cardiac motion is so fast that we need this. If you have only 10 hertz resolution, we miss a lot of movements, a lot of valve close and opening. So, and the last image mode is the B mode, the brightness mode. This is the most common one. Here, as we had before, we have several lines which are not parallel anymore for the convex transducer, or for linear transducer could be parallel, and we just combine different A mode lines to one overall image. Here, the frame rate is reduced, since we have to reduce 200 line of sight roughly, or even more if you want to overcome the spacing of the piezo elements, and then we reduce our frame rate for the entire image to several tens of hertz. The example is okay, should be a movie, but it isn't. Okay, did everyone have an idea what is this? Or is someone not?
It's a kid, right?
Exactly.
Yeah.
Great. Okay, yeah, it's in ultrasound it's way easier to see structures if say moving all the time. So this is quite fun. Okay, we have the child. We have here the face, the nose, mouth. This is skull here. We have the arm. We have the chest here. If it's the movie, you see the beating heart. And we have the high reflection, exactly where we have high interfaces or strong interfaces between soft tissue and bones, here in the arm and the skull. We have no reflections in the fluid areas, we have no scatterer. And so we can create the ultrasound image based on what we still know from the ultrasound interactions. But we have also here a lot of holes in the brain. Did anyone has a clear clue what is the cause for these holes? Why this is black here? Water. Yeah, water could be, yes. Okay, this is a really healthy boy. Meanwhile, he's 18. And this is kind of image artifact. This black area here. The area white could be also water, because here we have also water. And therefore, I want to briefly go through two artifacts in the entire zoo of artifacts for ultrasound, because yeah, it's important that this is a healthy one and not someone who has a lot of fluid in the brain. So the most important one is acoustic shadowing. Here in an example for gallbladder stones, we have these stones here, these three-line things, and the gallbladder stones has either a high absorption or have high reflection. Both came to the same result. We don't have any transmission in the brain. And therefore, we don't receive any signals, and it's displayed as black. So this happens as solid structures or high absorbing structures. In this specific image, they are bright, but there exists also image where they are dark. The opposite one is acoustic enhancement. Here we have less absorbing structures, like the gallbladder or the vessel on the left side. And these less absorbing structures, in combination with the time gain compensation, was amplification to compensate the common absorption, will be over-enhanced, and therefore we see here is white. What's useful is to distinguish between solid and liquid structures, because they both can appear in the ultrasound image as dark areas. But yeah, the most important one is you have a lot of artifacts and you have to know these artifacts to read your ultrasound results. Yeah. Again, before we came to the function, to the last chapter for ultrasound, are there any questions regarding this imaging stuff? Okay, not. Then last part is again about functional ultrasound. Here we are interested in measuring the function, the blood velocity in the body, and this relies on the Doppler effect. We have ultrasound transducer, we have some moving particles in the blood, and we receive some echoes. And if you have moving particles, the ultrasound wave gets frequency shifted. This is indicated by the equation on the right side. Frequency shift is a function of the blood velocity, which is nice. And measure this velocity. It's also from the ultrasound frequency and from the angle between the ultrasound beam and the blood velocity. And at the end, we see that our blood velocity is roughly in the range of meter per second. We have frequencies in kilohertz range, and therefore we have frequency shift in the audible range. And this is what we all sometimes hear from ultrasound devices. Directly the frequency shift from your veins or arteries. So typical application is here to measure really the quantitative quantitative blood flow. We have here a small gate to select a specific depth. We have the direction of blood velocity, which is adjusted manually, correct for this theta angle, and then we see in the bottom blood velocity, up to 1 meter per second over the cardiac cycle, and then we can provide some quantitative values, measure the peak or high, the second peak value, time duration between the first, second peak, and so on to characterize some mostly cardiac or stenosis, everything else. This is called the pulse wave Doppler ultrasound, the most common technique. But we don't only have this one is point measurement. There's also a second technique which is called color flow, sometimes color Doppler, where we create an image of the blood velocity distribution. And this has first purpose is to identify different structures. Here, for example, we see veins and arteries. By knowing that everything is red colored, there's a velocity projection towards the transducer. We have here kind of steered beam. We see the projection, the upper one has a small component towards the transducer here. We are not able to detect the lateral component. Therefore, we assume that the velocity goes from left to right. Blue structures have a velocity away from the transducer. In this specific case, means to the left bottom. It means that the vein is low from right to left, and we can identify or distinguish veins from arteries. This is the first purpose. The second purpose is to insert the video again, hopefully. Oh, yeah. Okay. Here we have some kind of stenosis, and we see a vertex where we have a reverse flow coded by the color, and we can detect this vertex, characterize this vertex by color flow imaging much easier than we have instead of having the point measurement of the quantitative values. Okay, so this was the short introduction about ultrasound. We will come to the next part. If there are any questions about content.
Isn't the measurements with Doppler effect dependent on the cross-section area of the vessel?
You measure a little, you measure within this range here from here to here. So you try to avoid the outer part of the vessel, so the flow in the middle of the vessel is faster than the outer part.
So you're measuring, but still the velocity would be.
You measure kind of average velocity within this range. If this was, you measure an average velocity within this depth range, as this is the question.
Yeah, but in different cross sections, in different vessels, it will be different, though.
Yes, if you have a smaller vessel, you assume a different flow
Yeah.
compared to the bigger one.
And can you compare between those measurements? Or is it just like correspondent only to one?
I think it's not common to calculate the diameter and correct for this. More that you have just a value, okay, they there's thresholds for the absolute values for the velocity or chaotic artery vortices, for example, but not a global threshold for the entire body. Since the vessel has more or less, okay, you also calculate the diameter of the vessel as an independent parameter, but you don't correct the velocity.
Mm.
That means, okay, if your vessel is dilated over a certain threshold, then with the indication for things. And maybe in addition or separately, if you have a specific flow pattern here, either to qualitative in things, okay, you have a second or third peak, or quantitative that you have seen in a certain time, then it's also an indication. Okay. Then we can go to the next second part. This is magnetic resonance imaging. And yeah, here everything is about magnetic properties. We have the magnetic properties hydrogen atoms. We have the magnetic properties for the entire scanner, the magnetic field for excitation and position. And also MRI is quite young techniques. That's roughly 93, and also is a comparison of what they achieved in the last years. It's impressive. If you compare the grain on the right side, you see how many details now required. And who is the quote here at the end. So the scanner consists of several different coils. We have high frequency coil, gradient coil, and the big magnet for the homogeneous magnetic field altogether, the entire device. And now we can have a look at going up in detail. So first is again the physics, the magnetic behavior of protons, and yeah, since we don't have the bat anymore, we have here the goose, which has also a magnetic sense, and so anyway. Yeah, first thing is that the human body consists of about 60% of water, therefore also the hydrogen atoms, with the most important one, proton in the middle. And this proton consists of a magnetic momentum and angular momentum, the angular momentum L, and the magnetic momentum mu. The ratio is the general magnetic ratio, in particular for the hydrogen atom, we have here the 42.6 megahertz per Tesla. So it's a characterization for this atom, which is used later because we have to match this frequency. Independent, we have the magnetic field, the external magnetic field in the scanner. It's realized here by the Helmholtz coils. And the Helmholtz coils have the advantage that we have a homogeneous field between the coils. It's called E0. It's just for definition, always along the z-axis, and typical field strength in the MRI is about 1.5, 3 Tesla. Meanwhile, they also start with 9 Tesla. And for comparison, the Earth magnetic field is way lower, 10 to the power of 5 with 48 microteslas. So if we bring both together, the proton and the external magnetic field, we see that the proton starts to with the position around the E field, the external field. The frequency is determined by the general magnetic ratio gamma and the external field B0, and then we came up with whatever we use for the magnetic field. But we only see this parallel orientation. We also observe anti-parallel behavior with two energy levels, the upper and lower, with a specific energy gap, and they have not always equal balance, so the number of up and down is not exactly the same. They have a Boltzmann distribution, and so we have a small difference. So this is a microscopic view. We go next step to a macroscopic view. The end we observe macroscopic behavior. We see that without an external magnetic field, the spins for each proton are quite random, so they cancel out each other. We don't have any net magnetization. If we now switch on the magnetic field, we see exactly this distribution, so some up or some parallel, some anti-parallel, and they have really small difference. So 1 minus 10 to the power minus 6. However, we have a lot of atoms indicated by the Avogadro constant in the body. So at the end, we see some net magnetization. This is the main thing. Since they're a little bit different in numbers, parallel, anti-parallel, we have the net magnetization. The net magnetization is in Z direction, so the net magnetization at 0 is orientated along Z. But we don't have any net magnetization in transversal orientation, so perpendicular to the Z-axis, perpendicular to the B0 field. And now we can go and start the second magnetic field, high frequency field, to start some resonance effects. This high frequency field is perpendicular to the original field B0, and it's rotating in the XY plane all the time with exactly the same frequency as in the mind for the lamp frequency to the German magnetic ratio. Therefore, it's important for this frequency and to adjust for this. If we start with this external magnetic field, our net magnetization M0 starts to rotate around B0 and also increase the angle here indicated by alpha, and goes far away and continuously move in the XY plane. After a certain time, this is a 90-degree flip, and we observe that we don't have any net magnetization like that. We have a pure net magnetization in the transversal direction, which is M0. And then we can observe what's happened after this short transversal magnetic field application. What's happened with the net magnetization? We switch off this transversal field. So this is shown here. We have two kinds of relaxation. One is spin lattice relaxation, indicated by the relaxation time T1, which means that our net magnetization slowly recovers over time with constant T1, and we come to the initial state we observed. We have a second relaxation, which is independent from the T1. This is the T2 relaxation, indicated by the T2 relaxation time, and this describes how the transversal magnetization is reduced over time. Again, they are independent, so we first see that the transversal magnetization is fading away, and later we observe directly one after each other, at a different time, it's a longer time, we observe that the axial magnetization recovers slowly, and it's not that MT and MZ adds to M0, but they are in this case a little bit independent. Just to get a feeling a little for this, first of all, the T1 relaxation time is quite longer. You see several hundreds of milliseconds for different kinds of tissues. They are obviously specific for each type of tissue, and the T2 time is several tenths milliseconds. Okay, before we start this image acquisition, is there anything unclear about this?
There's something called a T1 star or T2 star?
Yes, there is. I skipped this for a matter of time. This is another relaxation time which is even shorter than T2. Due to interaction, it faded away, but you can recover or undo this effect. This is done by the echo, this echo sequence. Yeah, they exist, you're right.
And I just have like a fundamental question. It's not possible to know the states. It's only possible to know the times, right? Like it's only possible to acquire the images when they're going back to their original state or the other way, right?
It's okay. What you observe at the end is only the transversal magnetization. This is the quantity you can measure. So go back here. This is happening in the background. What you see, or what you can observe is this one, but this is not directly observable because we just from the technical point we don't have access to the that magnetization. Was this your question?
So we just observe the magnetization as the molecules go back to or go to some equilibrium state.
Yeah, it has to be flipped out of the.
Right. Yeah, we with the fields, we flip them. They
Yes.
flip back and
Yes.
then we measure the change.
Yeah, this is what I try to describe this here.
Yes.
That
Yeah.
we go back to the initial state. This describes the MZ or the upper one, the longitudinal relaxation.
But we can't measure it before and after, like before we flip them and after.
Yes,
them.
we can't measure.
Okay.
Yeah, because again, we only see what's happened in the transversal orientation. And here, before we, or maybe at this point, so we have only Z magnetization. So what we can observe is MT, but MT is always zero here, independent how much the MT zero is in this specific case. And then we flip M0 and make it transversal, full transversal. So we don't have any Z magnetization at this moment. We have a full transversal magnetization. And this quantity in general, the transversal magnetization is observable. Therefore, yeah, we need this 90-degree flip pulse to make this visible.
Just a comment to the T2 star. This is related to the homogeneity of the magnetic field. You have a magnetic field which is not perfectly homogeneous, and different spin packets experience different magnetic fields, and they dephase in a different with a different speed. Therefore, the superposition of all these relaxing particles is even faster than the relaxation of the T2. So therefore, the T2 star is a magnetic field homogeneity effect, which can be reversed by an echo pulse.
Did you have some slides about this later? No. Okay. Then you have the backup slide about this, but yeah. Okay. Then we can go to image acquisition. And yeah, big problem is this takes a long time, and I want to don't go too much in the image acquisition part due to a matter of time. So the idea is, okay, we have the magnetic momentum of the proton, we have the external magnetic field, and in some way, in some black box, we can recover the distribution of the magnetic behavior, as you see on the right side, the image, or as a cube, its voxels. And yeah, without going into details, there are some important things to know for the next steps. So one is we don't have a single acquisition. It's not a one shot like a photography and then we have an image. It's the entire image consists of several single acquisitions, ones after each other. And they are characterized by two major properties for the image acquisition. One is the TE time. This is the time between our 90-degree flip angle, where we move our magnetization transversal orientation, and the image acquisition for each single acquisition. The second is the time between all the single repetitions or single acquisitions. This is the TR. And as I still mentioned, we only see the magnetization and the transversal orientation. So the image contrast, again, here we have this times. We have the TE time between the flip in the transversal plane. We have the image acquisition where we measure what happened in the transversal plane. And then we start the next image or sub-image acquisition and so on until we have a full information covered. And then we can reconstruct the image. So there are different types of contrast for our image. It's not like in ultrasound we have more or less only one image, which is of course dependent on the ultrasound frequency, but for the same frequency you observe more or less the same ones. So this describes two things. The net magnetization is characterized by the dashed line, the transversal magnetization characterized by the solid line, and I choose two different types of tissue, just randomly. The red tissue is a specific M0 magnetization with a specific T1 relaxation time and T2 relaxation time, and tissue marked in blue is different property. So after the 90-degree push flip angle here, everything is flipped in the transversal direction, and now we have slowly recovered the Z magnetization. If we wait for a really long time with TR, then you have a full recovery of MZ. And we start really that MZ is the same as 0. Then we start our second flip 90 degrees. So basically what we do in the first thing, and everything goes in transversal. Here, if we do really short TE, so between the flip angle and the position, we don't spend too much time, then we can see a more or less unbiased transversal magnetization, which is highly dependent on the M0, but less dependent on the relaxation. But it's just a weighting, it's not a quantitative measurement. So it's still affected a little bit by T2, by the relaxation of the solid line, but not so much. Therefore, it's proton density rated, which is similar to M0. It's a little bit. Okay, this is the first image contrast. The second one, or maybe, are there any questions for this? Because we need it for the next two. Okay, second one is the T2 weighted image contrast. The left part is the same. You full recover the M0 magnetization, but then we wait for a longer TE time. So between the 90-degree flip and the recovery, spend a little time. What happens this time is that the T2 realization slowly decrease our transversal magnetization. And at the end, the effect of the T2 time overcompensates what we have in the beginning for different M0s. Therefore, it's T2 weighted. Tissue with a longer T2 time, the blue one, has a higher value at the end, higher signal we receive compared to the tissue in red, which has a shorter T2 time. Are there any questions on this?
For a contrast agent external, what property is better to have, a T1 or a T2?
I don't know exactly. What did you know for contrast agent in MRI? Is it T1 or T2 weighted image?
It's a T2 weighted image with gadolinium-based contrast agent. You see it right. Yeah. Normally, relaxation times can only be shortened, right? You can never prolong an relaxation time, right? So, and if T1 is shortened and you have a T1 weighted sequence, then the intensity gets brighter.